Hello. Hey everyone. So, as said before, I'm Alex Sharp. I'm from RyanVM. Just a quick show of hands. Who's heard of us? Okay. So we're a sponsor of the event. Amongst other things, everyone here gets, I think, $100 worth of free credit just for being here. We also sponsored Code Wars and a few other things. But long story short, RyanVM is an engineering organization. We're cool because we turn supercomputing tech, and we basically turn it into a cloud. So we get to play around with terabits worth of switching and petabytes worth of storage, and it's a really cool job. Although you could say I'm slightly biased given I'm a founder. But anyways, so this is, the talk's called Big Data in Python. Now, just to preempt a few questions, you'll notice that there isn't actually any Python code in this talk. That's because there was initially Python code. However, when I was going through and when I was doing it, I went through and start off, and you're just like, so am I going to go through and do a standard sort of talk with Disco and MapReduce? And I said, well, I'm going to move a bit further back, and I'm going to show something that's hopefully a little more interesting to you guys. So first off, what is big data? It's been hyped. It can mean almost whatever you feel like. So things like PageRank, which is, by the way, damn cool. Who has read the paper? PageRank paper? Yeah, it's essentially how do you win at searching by finding the eigenvalues of a squillion by squillion matrix. It's really kind of cool to work out how it goes from pure maths to something very real. In much the same way as, say, nuclear sims, you can't say that LLNL's cluster is not a big data job. Like, it's pretty huge. However, the bit that I'm going to start off with is, it's essentially, I'm going over a few papers that were published. I'm not naming names here, however, if you're interested, come talk to me after and I'll show them to you. So the major, well, just go back a little bit. Data analysis at scale is where you see lots of big data jobs. Things like Facebook. Facebook really cares who you are. Facebook really cares who your real friends are, not your Facebook friends, because even they know they're not real friends. Similarly, for example, Google. Like, you might be known under a whole bunch of pseudonyms, but working out who is the same person is a very interesting piece of information. However, the bit that I'm going to go through and show you is a really cool one, and it's, are you a telemarketer? Now, you might go through and say, well, wait, what? But this is a very important piece of information because telemarketers, well, they're horrible. Not put too fine a point on it, but for the big telcos, they go through and they cause lots of abuse complaints and all the rest. So finding them is a big challenge. So big data, data analysis at scale. You're a giant telco, you're trying to answer a very simple question in a very restricted domain, very restricted domain. You know what your data is looking like coming in, and you're trying to do it, well, you're trying to do it well enough that you're not going to go bankrupt trying to do it, which is in some ways rather hard. So in this case, are you a telemarketer? And the thing I'm going to be explaining is, well, two really interesting algorithms. For one, counting how many people you've called, and two, how many unique people you've called. And I do this without using a counter. So think about that for a second. And yeah, so the standard domain, in this case, a big telco is doing this. So they need it across all their squillions of users. They're doing it on embedded hardware. And yeah, so and at the end of the day, this needs to be done cheaply because otherwise it's just cheaper to just not use the information at all and just deal with the abuse. First things first, a very important thing about big data is you need to know your distributions. So I'm kind of sorry, but there will be some maths in here. There's really no way to get around it because it's a very maths-heavy subject. So this is a Pareto distribution. I use it as just a general, so there are the distributions that look like this, where, like for example, if you're looking at, say, number of people, okay, I really should have brought a laser pointer. But number of people that someone is calling and percentile. So you'll find there are some people who call absolutely everyone, and most people call no one. This is very common. You see this all the time. You see it in, say, in big networks. There's all of the, so everyone's talking to Google, but no one's talking to my website. Common sort of problem. But knowing the distributions then means that you can make all sorts of assumptions that will really help you out, and I'll show it later on with a really cool paper by, actually I will name this one, Google, at the end. So this is the other one, normal distribution. And you have to be very careful here, because, okay, so here, who here knows that if you average a whole bunch of numbers, they eventually become normal? Who here has done like basic stats? Okay, you need to be very careful with what numbers you're averaging, because otherwise you can end up with some very interesting results. That being said, normal distributions are awesome and they are your friend. Well, certainly my friend. Anyways, so okay, so first thing. Now, okay, first off, who noticed that this thing doesn't actually have a counter? Okay, wait. Okay, there is no, like, standard example, you use memcached or whatever, you pull in a value, you increment the value, and you write it back out. That's the way you do a counter, right? Like, that's the canonical standard way of doing this. The problem is if you're going through and doing this, like if I read this counter and then someone else reads this counter, then you can end up with us both trying to write at the same time. You have race conditions, and then if you try to solve the race conditions, then you end up with other concurrency issues. You have problems scaling it out. And it's just generally really hard on your actual data stores. You have all sorts of really nasty problems. So you have things like this. So, you go through, you take a, this happens all the time in big data, by the way. You read someone's paper, and in about 4 lines, they'll go through and they'll show really easy steps, and you take a look, and you're just like, I have no idea what that guy just did. This is one of those. So you start off, he's like, choose some random number, count the number of leading zeros, and keep a track of the maximum. And you're just like, how on earth does that count the number of things? Like, seriously, who's thinking that right now? How on earth does this work? Okay. This is cool. So, because you're counting number of leading zeros, so these are all random numbers, so the chance that the bit right at the end is 0 is 50-50. So 50, like 50% 0, 50% 1. Same as, so you have a 50% chance, if you just look at 1, that you'll receive 1 from your count. Similarly, the probability of there being 2 leading zeros is a quarter, 3 is an 1/8, 4 is a 16th, and so on and so forth. So, like, let me just give you an example. If I've actually run this algorithm, say, 1,000,000 times, what is the probability that I have only ever encountered, say, only 1 leading zero? And the answer is it's very, very small. So, yeah, it's a stats hack. You'll see a lot of these. But in this case, you're using the fact that all of these things have different probabilities to give you the data that you need to find very, very approximately where it goes. Yeah?
Is that binary?
Oh yes, yes. So you deal with it in the binary representation, and use 2 to the c as the estimate. Now, generally, like 2 to the c, okay, it'll give you a actually rather horrible estimate if you do it once. So you go through, and you get a whole bunch of them, and you average them, because that's what you do if you want to make it more accurate. Yeah? Okay, hands up if you think averaging is the right thing to do. Good answer. Don't average this. You'll end up with absolutely weird and wonderful answers. What you need to do, if you look at the paper, is you need to take a bias-corrected harmonic mean, which is, by the way, absolutely horrible. They have this massive formula and all the rest. However, you can just take the median, which is good enough. And by the way, you see that a lot. Oh, just a random thing. If you want to troll data scientists, get into a mean versus median debate. Just, yeah. However, so median is just standard, and that's simply because when you do this, like, you end up with some of your estimates end up too high, some of them end up too low, and because it's exponentially increasing, the mean gets weighted too far based on the very high elements. So it doesn't properly respect it. Harmonic means are a bit better for this, and the problem is that, as you'll see with stats, with say most of these big data things, it's usually cheaper to get things that are wrong and then make them right than it is to actually get the right things in the first place. So in this case, this is a very cheap counter. Like, you just need to keep track of a maximum, which is one of the cheapest operations possible. You can run it all in the background. It's really nice. But then you do all the extra work on the other side to actually turn counters into meaningful data. However, the really cool thing is called MML, so method of maximum likelihood. So harmonic means and all the rest, okay, those are fairly standard things. MML is a really cool stats method where it's essentially, so these counters have these values. Well, out of all of the possible things that could have happened in the real world, what is the most likely thing in the real world that would cause the counters to have the values that they have? It's very nice. It is, well, it's not that horrible, but it's still horrible to make. But if you want it for the absolute minimum sort of cost, that's what you want. Second thing, how many unique people have you called? Okay, who here knows what a hash function is? Okay, for the 2.5 people who haven't, a hash function, like for example, hash of the person, is you take this person and you turn them into a random number. Now, just a quick question, what were you using in the last slide? We were using random numbers, yeah? Yeah, because like the first step was take a random number. So now you're saying, well, how does this work with uniques? The answer is, of course, if you take a quick look at the previous algorithm, you'll know that if you run it with the same random number twice, it can't possibly change. And the reason for that's actually fairly simple. If I have a number, it can't suddenly get more leading zeros into it simply because you show it to me twice. Because it has that many leading zeros. It just doesn't. Maths don't work that way. So because of that, when you run this using the hash, it only counts the number of unique people, which I think is rather quite. I think that's cool. Like out of all the things, you see lots of things where it's just like, that guy has got it figured out. Like whoever came up with that, I'm going to buy that guy a beer and a cake because he just solved one of my problems. But yeah, so that's unique people. And of course, the problem is then, so how do we store the data? So this is how many people have you called? So that is like, well, there's Pareto or log normal. I'm reasonably sure that it's actually something else called the Zimpf distribution. You should Wikipedia that. It's pretty damn cool. However, they all look roughly the same. And the thing is that most of your counters are going to be near zero because most people don't call anyone. A sad but true fact. So if we just store the same number of bits for all of them, then all of the counters are going to be massively oversized, yeah? So, well, what can we do for this? Like, you're not going to store stuff compressed in memory because it's really not going to help you that much. What do you do? And the answer is, of course, you call Google. They, like, seriously, the Google guys, they know so much. But yeah, now for something completely different. Unary encoding, and you're just like, what on earth does that have to do with anything else? Can I hear that from someone? Oh, okay, no. So it does make sense. Try it, give another slide. So unary encoding is essentially like, so let's say I'm representing 1. It's like, oh, I'm using if you use a slightly different representation. 1 is say, it's what binary would be if it had no 0. That's one way of thinking about it. You have 1, and you have to represent all numbers just using 1. So it's like 1, 1, 1, 1, 1, 1, and so on. But yeah, so how do you store these counters? Okay. That H is a hash function, and you use a giant bit array. So the answer to the previous question is that yes, you can compress it. You compress it by sharing the bits. I kid you not, you share the bits between the counters, and then you deal with the slight false positive. Like it makes your counts slightly less accurate, but on the other hand, these were like random estimate counts anyway. So making it slightly less accurate really doesn't matter if it means that we can store more counters. So overall, you can make it more accurate and use less space. I know, I thought that was pretty damn awesome, but then I'm a bit of a nerd, in case you haven't noticed. So okay, so you have this hash function, and it's essentially, given the name of the counter and a bit position, work out where in the bit array it should be. So for counter Joe and bit position 1, you should be in bit position 10. So you go through and you look at the 10th bit, and you work out if it's set or what have you. Now, the interesting bit is, say, on set, you go through and you say, well, so let's say k is a counter value, and let's say we say k is 5. I go through and I say, well, what for counter Joe, where should the first bit be? First bit should be in, say, bit 2. Set bit 2, and then you just keep going until you go up to, I think it was bit 5, I think I said, because 5 was the value of the counter, and the number of counter is 5. Sorry, I just had to do that. So because you do that, the downside is that if you're setting bits that are the same bits as somebody else's counter, then the other counter might miscount and might be considered larger than it really should be. But on the other hand, because you're sharing bits, because most of your counters are going to be very low values, you can then use many fewer bits. So that's essentially where they're coming from. So similarly, on read, you simply keep counting until you find a 0. So where's my first bit? It's in bit 2, that's a 1. Then the next one should be in bit 4, that's a 1. Oh, the next one's a 0. Well, okay, that's it. My count is only 2. And then you do the stuff that I mentioned earlier on to actually turn it into a real number. It's at this stage when I tell you once again that it is usually easier to get lots of data and then lots of noisy data and then make sense of it at the end rather than trying to collect really clean data. So for example, with the earlier algorithms, those are very cheap to run. They're very cheap to store. You only need a couple of bits. Like for example, let's say that you're running a counter. Let's say you need to count up to 4 billion. 1, you need to increment a counter 4 billion times, which takes some time. 2, you need to store 32 bits. 32 bits is a lot more than, what is it, like 5 or 6, which is log of 32. But yeah, so it's essentially, you store less data, you need fewer, you have fewer operations, and the operations you're trying to do are cheaper. But anyways, so that part was just analytics. So that was, actually, I don't name them, but yeah, large telco, UK telco, they had problems with a whole bunch of telemarketers coming in with their SIP trunk. They need to develop some algorithms to go through and efficiently find them on their massively distributed infrastructure. And so they did. And I kind of modified it a little bit to make it an easier example, mostly because those methods aren't exactly the methods that you would use in a real life scenario, but they're easy enough for me to go through and show, and they're damn cool. And they're damn cool is also a very good reason why I'm showing them to you. By the way, hands up, who thinks that those algorithms were damn cool? Oh yeah? Everyone knows MapReduce. If you want a MapReduce tutorial, Google MapReduce. There are 1,001 of those. What people tend to forget is that there's more to big data than MapReduce. So let's just say you're trying to sum all these things. Standard way is you go through and you get like first number, add second number, add third number, whatever. That takes some time. It takes O(n) time. And that's the problem. When you have a big data set, well, your data set's huge. So because it's that large, it then takes forever to go through and run these operations on. So you can do things like this. This is an addition tree, but it's an example of a more widely used technique. The more widely used technique is quite nicely known as property hacks. They're called property hacks because you use the properties of your data set and the things you're trying to do in order to break it into little pieces that you can then reintegrate using other functions in some more efficient way than you would just generally think to do. One example of this is actually shown in Google's PageRank paper and also in the Stanford Big Data book. Actually, I'm not sure if it's in the paper, but it's definitely in the book, where they go through and they take this absolutely massive matrix and they go through and they cut it into slices and they distribute it. Now, in that particular case, they use MapReduce, but the end result is the same. They use multiple rounds of MapReduce and they abuse the properties of, it's not even matrix multiplication level, it was the various things that were trying to do to the matrices that they could go through and integrate it and end up with the right result. So in this case, this, like, a tree like this means you can go through and say add large numbers of numbers in log n time. So you guys can probably pretty easily see that. But the more general case is by far the cooler case. But yeah, I just wanted to let you guys know that there is more to distributed computing than MapReduce, because it gets massively used, like everybody uses it and it gets a bit hyped. Finally, okay, why Python? Why would you use Python for this? Python is damn awesome. Next. Python is damn awesome. Cython, if you haven't used it, Cython is damn awesome, mostly because you can use Python code, or restricted Python code, compile it into C. RPy is damn awesome for doing data analytics. NumPy and SciPy are just damn awesome. Erlport lets you connect as an Erlang node. And that is really awesome because lots of the larger, like for example, the insides of telcos and all of those sorts of things, those are all Erlang. So going through and being able to connect to the end of it is very useful. Similarly, ZeroMQ, lots of, say, HFT stuff is all ZeroMQ InfiniBand on the inside. So being able to just attach to that and use that is very useful. Python is by far the nicest glue language around. And it's more than a glue language, it's a really awesome language. So that's why you should use Python for big data work. Because in case you haven't noticed, the actual algorithms earlier on, they're very simple. And being able to very easily iterate and what have you is, well, one of the great selling points of Python, as well as its awesome libraries. So, interesting stuff, won't go into this. Some of the earlier things are called hyper-log-log counters. The general class is called log-log counters. The hyper stuff is kind of weird, but very cool. The Stanford Big Data book is awesome. As books go, if you're interested in this sort of stuff, you should definitely read that book. The rest of it is just other cool stuff that people generally don't know. Thanks.
Thank you.
Previous slide?
Sorry. Any questions?
If anyone's interested, I can go into some of these while I'm talking. Anyone interested in a rough overview of what these are? Okay. Two-left hashing is damn awesome. I say that a lot, but that's because lots of stuff is awesome. So two-left hashing basically means that if you take a large set of things, you pick two items at random, and you put your thing in the least loaded one, you are theta log n optimal in terms of your load balancing. Okay, I'm not, like, that is an absolutely massive achievement, because typically it would require all sorts of complex things and horrible hacks to get even close to that. And like log n is close enough to 0.1 that you just don't care. And just choosing 2 and moving to the left, well, actually, yeah, bit of homework. Why do you choose the left one? There is a thesis on that. It is a thesis, but it's easy enough to read. It has an overview of all the things. Talk to me if you want it. But it's really cool how, for some reason, always choosing the left one, in the case of a tie, gives you a more optimal result. And yes, that stuff's cool. Stanford Big Data book is damn cool. It just has lots and lots of stuff in it. Hyper-log-log counters are kind of the things that I showed you in the beginning, but not quite. It's an adaptation. Bloom filters. Bloom filters belong in the more general set of AMQ, so approximate membership query. So if I have a thing, okay, who has used sets in Python before? Sets. Or done X in Y? Bloom filters are a damn efficient way to work out is X in Y. So they can store like any particular element, no matter what it is, int, string, whatever. They can do that in, I think the theoretical max is 1.44 bits, no matter what it is. However, generally it's more like 4 bits, which is still damn awesome. The only downside is that it has false positives, but no false negatives. That is to say, it will occasionally tell you that things are in there that aren't in there, but it will never tell you that something is not in there when it in fact is. So those things are cool. They have been superseded. This is the good thing about big data, like good and bad, is that stuff is happening continuously all around the world. So Bloom filters, everyone loves Bloom filters. There's a squillion types, and they run everything. They're if you Google them, you'll find them. You'll find applications in all sorts of things. They were superseded in 2011 for the applications where the Bloom filter is larger than RAM by quotient filters. That only came out in like 2011. There are 2 papers mentioning it at the moment. So there are things like, there is no Python implementation for it. You can't even, if you do a simple Google search, you won't even find example code on it. That's how new this stuff is. But it's really quite cool. It's, I think, 30 or 40 times faster than Bloom filters. So stuff in the big data sort of space is going through, it's moving really fast. You take a look at it and it looks kind of scary, but if you take the time and you have a look at it, most of the stuff isn't that bad. Like if you look at the hyperloglog counters paper is kind of nasty. I may or may not end up publishing something that's a bit easier to understand. But the actual, you guys would get me. You take one look at it and you're like, how does this work? But then when you have a couple minutes to have a think about it, it's like, oh yeah, it's you need to make sure that you're not scared off by the initial step, because even if it has unfamiliar notation or whatever, most of this stuff isn't that hard. But anyways, those questions, sorry. So I really love this stuff, so.
We'll have time for maybe just one question, if there are any. Yeah.
Thank you for the talk. You mentioned that if you do it many, many times, and eventually you will get it to be more accurate.
Yep.
But you didn't actually mention, in practice, how do you make it accurate?
Okay. Accurate is an interesting term. Accurate depends on what you're trying to use it for. Like, let me just give you an example. Wait, and here. If you're trying to work out if someone is sitting over here, or if they're sitting over here, you don't need to be very accurate at all. That's very easy for you. However, if you're trying to differentiate 2 people who are really close together, then you need a lot more accuracy. However, I think the 2 major ones are method of maximum likelihood, and I think it's minimization of entropy is the other one. Pick up a stats textbook. It's usually taught fairly easily. It's not that complicated, but usually use those sorts of methods on large numbers of approximate counters.
So you eventually do have some kind of error margin. You just iterate until you satisfy your requirements. So you say, that's accurate enough, I can stop here. Is that how you work?
It depends on what you're doing. Oh, also, I should make another shout out. Who here knows Bayes? B-A-Y-E-S. Okay, the guys who don't, Bayes is very useful, and you should just Google it. I know, it gets a bit of hype as being hard to understand. If you find a source that isn't a pure maths textbook, by the way, don't learn this from pure maths textbook. You'll be fine. But yeah, so in terms of how you know how accurate's accurate enough, it usually just depends on what your bounds are. You try it out. That you can do lots of modeling. There's lots of modeling, lots of stats stuff. There's also a whole bunch of interesting things you can do. Like for example, if you know what your internal distributions were, you can feed that information into your model to make your model more accurate. So then you'll need fewer counters. So you can do cool stuff like that. Yeah. Anyways.
Thank you very much. We're out of time, but I'd like to present you with some coffee beans and a mug from PyCon Australia. Thank you very much.